Hello everyone. Thank you for being able to come for our presentation. As Caroline introduced us to us, the main theme of our project is the removal of carbon dioxide from the flue gas of a coal-fired power plant, and also to design the most economical way to reuse some of the flue gas components. Our project was done under the supervision of Mr. Chris Van Driel, who's a professional engineer at Stantec Consulting, and by Dr. Geeta Benrich, our professor. As part of the project objectives for our client NOx, we were to design a process for a 450 megawatt coal-fired power plant, and also a flue gas cleaning system in order to remove contaminants from the flue gas, and also a carbon dioxide storage system. We also had to demonstrate on a pilot scale level an economically viable and an environmentally friendly way to reuse the carbon dioxide being extracted from the coal-fired power plant at a rate of 1% of the total flue gas output. The reason why we are proposing to reuse carbon dioxide is because by the year 2015, it is expected that a legislation would be passed at federal level where carbon dioxide emissions for a plant of similar nature would be capped at about 3.3 million tons a year. Therefore, for a 450 megawatt coal-fired power plant, which on an average emits about 5.5 million tons of CO2 each year, the power plant corporation can be expected to pay about $33 million each year. Therefore, by finding a way to reuse the carbon dioxide, the power plant would be able to save up to $33 million annually. And the way we are proposing to reuse carbon dioxide is by producing biodiesel from it. Biodiesel can be produced by algae growth, because algae is a natural organism that is able to consume carbon dioxide and produce the biological compound of lipids from which biodiesel can be produced. Biodiesel as a fuel has many advantages. Firstly, it virtually contains no sulfur or other aromatic compounds which could harm the environment. Also, when used in conventional diesel engines, there would be the substantial reduction of unburned hydrocarbons, carbon monoxide, and other particulate matter. We expect that the biodiesel price could vary between $3 to $5 within the recent future. This figure is below the current gasoline and diesel price, which is somewhere between $4.50 and over $5 per gallon. To sustain the demand for biodiesel, there has to be a substantial demand for diesel from crude oil as well, because biodiesel as a fuel is being used such that it is blended with diesel at ratio of 20% biodiesel and 80% diesel, conventional diesel. It is expected that global diesel can have a demand that is going to rise substantially, because as a fuel for vehicles, diesel provides way more mileage than gasoline, and also over the recent years, newer diesel engine technologies are able to burn diesel fuel way more cleanly. Here is the proposed plant location at the NB Power's coal-fired power plant in Bellevue, New Brunswick. This is the main facility of the coal-fired power plant. We have noticed several advantages of the plant being chosen at Beldoon. Some of them being the vast amount of land that is available for further development, which is about 10,000 acres. That is the empty green space that you can see around the power plant facility. There is also the easy delivery of raw materials through the port of Beldoon. The port is this facility over here, just at the Scheller Bay. And also the algae process requires a lot of water, for which the ocean water can be pumped. So the biodiesel being produced from the 450 megawatt coal-fired power plant is almost pure at 99.8%. The diesel production is being measured for 1% of the carbon dioxide being produced on an annual basis. The maximum revenue that we are estimating is about $62 million each year at a selling price of $3.50 per gallon of biodiesel, and the net profit is estimated at $27 million. Before we talk about a detailed description of the overall process, these are the diagrams that briefly summarizes it. The flue gas being generated at the power plant will be sent to the flue gas treatment system, where the contaminants will be removed, and the flue gas will then be sent to the carbon capture system designed by NOx, where carbon dioxide will be separated, and from there it will be sent for algae cultivation. And after the algae has absorbed the carbon dioxide and synthesized it, biodiesel can be produced from the lipids. Now we'll be speaking in a detailed manner about the overall process from start to finish to generate the biodiesel. Firstly, this is the process flow diagram for the coal-fired power plant. I have highlighted the main equipment, which is the boiler, as in the blue outline. Also outlined are the economizer and the preheater, because conventionally all these three equipments are joined together, they're not separated. However, I've separated it for clarity and explanation. Also, the other main equipment are the 4 turbines, which are the 4 figures on top. And now we will focus on the flue gas generation process. To generate the flue gas, at first coal will be unloaded from the ship and then sent to the coal yard. Based on the power plant's requirement, coal will first be crushed and pulverized and then mixed with air. Coal will be pulverized to as fine as possible in order for efficient combustion, and then it will be sprayed into the furnace of the boiler, where it will be combusted. The flue gas produced after the combustion process will be used to turn water into steam. The flue gas will then flow through the economizer, which is a form of a preheater, where it will preheat the incoming boiler feed water. After that, it flows into the SCR system, which is called selective catalytic reactor, which removes the NOx content within the flue gas. A detailed mechanism of the SCR will be explained by Mr. Amin Bagheri. After the SCR, the flue gas will flow into the preheater, where it will preheat the incoming air, incoming combustion air. The flue gas stream has been outlined in this dark black line in order to emphasize the point that it is the main stream that we are focusing on to generate the future products. And here is the steam cycle. As mentioned in the previous slide, the heat from the flue gas will be used to turn water into steam. The steam will then first flow to the high pressure turbine or the HP turbine, after which it will be sent back to the boiler to be reheated again. The reheat produced will then go to the intermediate pressure turbine, after which it will flow to the low pressure turbine and then followed by the condenser, where it will condense. And then it will be joined by fresh makeup water and then it will be pumped through the condensate pump into a series of preheaters called the lower pressure heaters or the LP heaters. The boiler feed water will then be deaerated at the deaerator to remove dissolved oxygen in order to prevent corrosion along the boiler feed water tubes. After that, it will be pumped through a series of higher pressure heaters where again preheating of boiler feed water takes place. And the final preheating stage is at the economizer, after which it will flow into the steam drum, and then the water will then be converted to steam, and this cycle will continue. Now Amin will speak about the flue gas treatment system.
So here's the process flow diagram for flue gas capture system. As you can see, the main stream is highlighted in black, and that's the flue gas flowing through the process. The flue gas will flow through the SCR reactor to remove the nitrogen oxides content of the flue gas, and then through the electrostatic precipitator to remove the ash particles, and then through the wet flue gas desulfurization unit to remove the sulfur dioxide contents, and then through the NOx to capture CO2. So I'm going to talk in details for each section. The first part is the SCR reactor, the NOx removal. So in the nitrogen oxides control section, we are using a selective catalytic reactor. The flue gas from the power plant will be mixed with the air and ammonia mixture upstream of the SCR reactor. This mixture will inject it into the flue gas stream, and it will react inside the SCR reactor to produce nitrogen and water vapor, which are inert and can be free to the environment. The SCR reactor will use a honeycomb-shaped catalyst, and the material of the catalyst is vanadium pentoxide combined with the tungsten and molybdenum oxide, and it's on the titanium dioxide carriers. The flue gas from the SCR reactor will be passed through the air preheaters to preheat the air before going to the boiler going to the boiler for the combustion process, and then it will be sent to the electrostatic precipitator. The SCR and the air preheaters are part of the boiler, and they will be retrofitted to the side of the boiler. So the flue gas from the SCR reactor will flow to the electrostatic precipitator to remove the ash particles. The removed ash will be stored in the land to be sold to the cement and concrete production companies. And flue gas will flow to the wet flue gas desulfurization unit to remove the SO2 particles. As you can see the blower here, we use a blower to maintain the pressure in the pipelines to just enough to send the flue gas out of the stack. So here's a process flow diagram for the wet flue gas desulfurization unit to remove the SO2 particles. The flue gas from the electrostatic precipitator will mix with the limestone slurry, and it will react in the absorption tower here with the using chemical absorption. We achieve 95% SO2 removal. The reaction of SO2 and limestone will produce gypsum. The gypsum product will, in type of slurry, will flow to the hydrocyclone here, which removes the purge stream, which is a liquid waste, contains chloride and metals, which have to be removed before sending back to the environment. And solid gypsum will send to the vacuum filter, which is removing the water to set by the requirements from the clients. The solid gypsum will be stored in the land to be given away to the wallboard production companies. The liquid purge stream will flow to the liquid waste treatment plant, which I will explain in a minute, and the flue gas will flow to the NOx to capture CO2. So the liquid waste treatment plant, we are using a zero liquid discharge. The environmental regulations regarding the liquid waste from the power plants is becoming very stringent these days, and so more of the industrial companies are moving through the zero liquid discharge, which no water will be sent to the environment. So we're using an indirect fire rotary dryer. The liquid waste stream from the wet flue gas desulfurization unit will flow to the indirect fire rotary dryer, which evaporates the water content of the liquid waste, and it will be sent to the pond heat exchanger to heat up the water in the algae process, which George is going to explain in a minute. And the solid waste can be safely landfilled. As for the fuel for the indirect fire rotary dryer, we're using the glycerol, which is a co-product from the biodiesel production process. And as there is no market for this glycerol right now, we're using it as a fuel in indirect fire rotary dryer to cut down the utility costs for the plant. The flue gas from the combustion process of the glycerol will be sent to the NOx process. So here's the NOx process. As NOx currently is working as a pilot scale, it processes only 1% of the flue gas. The rest of the flue gas will be sent to the stack and to the environment. So NOx will separate the nitrogen, CO2, and water vapor content of the flue gas. This CO2 will be sent to the algae pond to produce lipids. And George is going to explain in a minute. So as I explained, these are the contaminants that are produced in the power plant by the power generation. And we estimated by 1 megawatt hour power production, 860 kilogram of CO2 will be produced, 2 kilogram of nitrogen oxides, 16 kilogram of sulfur dioxide, and 15 kilogram of ash, which has to be treated before sending back to the environment. And this is the proposed solution, as I explained. And between all of these, all of them are currently present at the Baladun power plant, except the selective catalytic reactor, which has to be retrofitted to the side of the boiler. So George now will talk about the proposed design process for the CO2.
So what I'd like to show you is the decision-making chart that we initially applied for the CO2 storage option. So as you can see here, we have what's shown in green is the option that we picked in the end. So what we had was we thought about enhanced oil recovery, where we're using CO2, we are pumping CO2 into oil fields to enhance the oil recovery in oil fields. And then we also consider dry ice, where we're converting the carbon dioxide into solid form, and then it's used as a cooling agent. But both these options were not considered viable because we're producing a lot of carbon dioxide. So we decided to go with carbon dioxide recycling, so which is where they usually convert carbon dioxide into hydrocarbons. And we picked the algae fuel one because it can be used as sunlight and water to produce a variety of hydrocarbons. So here we have our basic overall process flow diagram for the biodiesel production plant. Before I get into the details of that, I would like to explain the basic science behind it. So what we have here is photosynthesis, which is used by plants and algae and bacteria to convert CO2 into organic material by using sunlight and nutrients. And the other basic science term is transesterification. So the algae oil, that is the lipids that are lipid content of the algae cell, it's actually called triglycerides. It's reacted with an alcohol to produce fatty acid esters and glycerol. So here we have the first part of our system, which is the algae pond, and we are blowing in the carbon dioxide into the open pond system. And what's happening is that there are carbonation sumps that are located inside the pond at a depth of approximately 1.2 meters, and these for effective CO2 transfer. And we're also we're using a 6-day batch process where we're growing the algae over a period of 6 days before we take it out. And because of we're trying to maintain a temperature of 25 degrees Celsius, and we're also using photosynthetic light because Belladune is in northern New Brunswick. So heating temperature and light will be a problem in the winter. And we're also using a secondary system where we're using hot condensate from the water treatment plant as a heat to heat the pond with a heat exchanger. So the algae and the water is pumped out every 6 days into a centrifuge filter. Now a centrifuge filter is a filter that uses centrifugation to separate the water from the algae, and the algae is then sent to a mixer where it is mixed with methanol before it enters the reactor. Now here we have the reactor system where it goes into its preheated heat exchanger, which is to 155 degrees Celsius before it enters the reactor. Now we are using a plug flow reactor that's operating at 280 degrees Celsius and 5 MPa. This is a supercritical reactor. So what's happening is that we're using, because the product stream is coming out at 280 degrees Celsius, we're using that to preheat the algae and the water that are going in. So after this, we're producing methanol, biodiesel, and glycerol. Now we're using adiabatic flash drums to vaporize the methanol out of the biodiesel and glycerol mixture, and we are condensing the methanol and we're sending it back into storage for reuse. And the glycerol, the co-product glycerol, is separated using adsorption columns, and so we're producing the biodiesel from this. And we're also using a second phase reactor system because all the algae oil hasn't been converted yet. So we're also using a second reactor system to improve conversion. And now Mr. Mina is going to talk about the economics.
So this is, I'm going to talk about the total capital investment for the proposed plant. The total capital investment divided to two sections for algae farm and biodiesel plant. The capital investment for algae farm divided into direct cost, indirect cost, and working capital. The direct cost, there are costs which are directly related to the production, such as operating, labor, raw material, and is $10.8 million. So indirect plant costs are the costs which are not directly related to the production, such as taxes and insurance. And as you can see, is $4.3 million. The working capital for algae farm is $2.3 million. So for biodiesel plant, the direct plant cost is $35 million. The indirect plant cost is $14.4 million. And working capital is $7.6 million. So total capital investment for the proposed plant is $74.4 million. So the net cash flow is expenditure minus earning. The operation cost for the proposed plant is $29 million, and the maximum revenue is $62 million. So cost of production for each liter of biodiesel is 40 cents per liter, and the revenue is 90 cents per liter. So annual profit before tax is $33 million, and annual profit after tax is $24.8 million. This is the cash flow analysis. So we calculate the payback period. The payback period is the time required for the plant to pay its original investment, which is 4.1 years before tax and 6.2 years after tax. The return on investment is ratio of the money gained relative to the amount of money spent, which is 12% before tax and 5% after tax. So we performed sensitivity analysis on the plant, which varying operating parameters by plus and minus 15%. As an example, if the price of diesel per liter goes up by 15%, the return of investment for the plant is changed to 10%. And if the price of diesel decreased by 15%, the return on investment is going to be around 0. So the next one is oil concentration. If the concentration of oil increased by 15%, the return on investment is going to be around 10%. And also if you decrease it by 15%, the return on investment is going to be around 0. So at higher variance, the return on investment increase, and at lower, the return on investment decrease. So the advantages of the process is practical option for CO2 storage, natural process, environmental friendly. Well, disadvantages is the land usage. So on behalf of Group 11 members, I would like to thank our client, Mr. Walton, President of Enovex, Dr. Benrich, Dr. Couturier, Mr. Van Driel, Belledon Power Plant staff, Mr. Fournier for the valuable feedback. Any questions? Sure.
How does the carbonation cell work in effectively absorbing carbon dioxide?
That's a good question, because that's the key part of our system, because we want to make sure that the carbon dioxide stays in the water. So what's happening there is that the carbonation sumps are, like the pond itself is only 30 centimeters in depth, but the carbonation sump is 1.2 meters in depth, and it's located inside the pond so that like it's absorbing, we have a counter flow of the water going in to the sump, and it's absorbing the CO2 that is going in, right? And so it's staying inside the water, it's not going outside into the atmosphere. So, does that answer it?
Thank you. So the CO2, once it enters the pond, is the system then closed off, or is it a continuous injection of CO2?
Is the in the morning we pump the CO2, and then so is like for 8-9 hours we pump the CO2 inside the pond.
And then your 6-day process begins?
Yeah, 6 days is a batch process. So every 6 days we take the water out, remove the algae, and we send it to the filter for.
And also, we also have the federal cap limit of 3.3 million tons per year, so as long as we keep it under that cap, that's good.
So would you continuously use the 1% CO2 stream, or would you need multiple ponds to maintain that usage?
Right now, we are designed for a multiple pond system, actually.
So how many ponds would you need?
8 ponds, and but they're each approximately 8 acres in size, so it comes up to a total of 64 acres.
Yeah.
What changes in future do you think can make this process more efficient?
Well, there are so many. Right now, the open pond have the excessive space requirement. Well, there are different kinds of ponds. They're under research, like photo bioreactors. There's the type which they design the shape, make it smaller. Other thing is just like, for example, grow genetically different types of algae to have different kinds of oil concentration. So these are ways to make the process efficient.
In the SCR reactor that you have catalyst, is there any blocking and pressure drop increase? And if yes, how do you do the maintenance job?
Yeah, in the SCR reactor, there are channels which the flue gas will flow through, and on the catalyst. And there would be, because the type of the SCR reactor that we have in the process, as I can show, is high gas SCR reactor. And which is here. And so it's high dust SCR reactor. By high dust, I mean it's before the electrostatic precipitator, which removes the dust particles. So there is there would be a chance to block in the SCR reactor. So we use soot blowers. That's on the regular basis. That's an online cleaning system to clean the catalyst channels using the soot blowers. And during the annual regular maintenance of the plant, we do the manual cleaning, and that is being done by the operators, and it's manually once a year. And so there are like two different types of SCR that we can have. This is the high dust configuration, and you can have a low dust configuration. The low dust configuration is after the wet flue gas desulfurization unit, which removes the particles and SO2 contents. So it's only nitrogen oxides and the CO2 which is left in the flue gas. The advantage of using a high dust SCR is that we can use the temperature of the flue gas to preheat the air before the boiler. But in the low dust SCR, we have to preheat the air before going to the SCR to react in the reaction. So that's why I use the high dust catalyst.
So in your economic analysis, you included the cost of the SCR?
Yeah,
Yeah.
with it.
You treat all the flue gas, the SCR, and then in the end you take the slipstream of 1%.
That's true, but the SCR has to be retrofitted to the side of the boiler, and that because it's a new capital investment, so we included it in the plant. But we are hoping the NOx would include the 100% of the flue gas. So in the future, it would be an equal investment.
It's going to be 1% of slipstream. So whatever the 640 kg of SO2, NO2 which you showed, is for the 640 mg per hour the flue gas stream. You take out that component of only take out that component pricing. You take that 1% slipstream for a ppm of SO2 and NO2 which comes to the system. Do you see that it is what is the break-even point in different economics of that?
Well, if having just 1% of the flue gas stream, that would reduce the concentration of the nitrogen oxides in the flue gas. So for sure, the size of the reactor would be less because of the size of the catalyst and size of the reactor is dependent on the concentration and the flow rate of the flue gas going inside the reactor. But for the SCR reactors, there's minimum requirement of having 2 catalyst layers. So that is, in that case, it wouldn't differ the size really much, but like just the height of the catalyst and the size of the catalyst would be different.
Sure.
You indicated that in New Brunswick, with sunlight and conditions and so on, you have to use synthetic light.
Yeah.
This represents parasitic load on the power plant. How much? Calculate that, 1% of the output of the plant will be used for.
You mean for heating up the?
The heating or converting the.
Is both of them. We are using heating coil to heat up the water, and also you're using the light for the winter time.
To extend the sunlight hours, because there's only during the winter there's only a few hours of sunlight, and to enhance the growth we need to get at least 7 or 8 hours of
How
sunlight.
many days in winter time do you do?
What's that?
How many days are you extending the reaction time?
For a few hours, like just like if it's if during the winter like there's only like you get only photosynthetic light for 4 to 5 hours at most. So then we're going to do it for another 3 or 4 hours. So because we've designed our operation so that we're going to be running it at for 8 to 10 hours, depending on if it's summer or winter. So, and then we're going to shut down the algae pond during the night because we cannot photosynthesis cannot occur without sunlight. So.
Are the ponds covered or are they closed? Or is the algae covered?
We're going to cover the ponds during the winter because it's going to be it's going to get affected by the snow.
Are they currently using this kind of plant anywhere?
Yeah, they have a plant in Israel, and they're in US and so many countries. And also, I guess U.S. military has a large production for the jet fuel. They started in 2010.
So your production's roughly 17 million gallons per year, because you guys said you're selling at $3.50 per gallon. Is that right? I was just wondering if you guys looked at your economic analysis, whether all of that could be consumed in the Belgium region or any of it could need to be shipped elsewhere.
Well, I guess we need to, well, some of them we can use it in Baladoon, but we have to ship it to other places as well.
What we consider was like getting tax credits for New Brunswick and just selling it within New Brunswick area. So like supporting the trucks and like getting fuel for the trucks that are transporting from Baladoon and areas like that.
I saw at one point you guys had, for each megawatt hour of production, you broke that down into, it was volumes or weights into the different components. So what I didn't see, I'm not sure, was take that one step further and translate that into cash out and cash in, so expenses, revenues, turn that into a profit. I'm sure I saw that, but that might be a really good economic ratio to focus on, help drive decisions that way. So per megawatt hour of energy production, how does that affect the cash flow in each of these different systems? So, but it doesn't relate to my next question, more of a comment. So my question relates to what this gentleman had to say about being a biological process and impacted by weather conditions and stuff like that, like Canada in winter. So are there places in the world, obviously there are, that would be better suited to this type of process? What would those places be, and how would that affect the economics?
Well, of course, well, the main thing for photosynthesis is light, and some places which they have more light and is warmer, so this process is going to be more economical, because we don't need to then put the like the light, synthetic light. We don't need to put the heating coil, so it's going to affect our cost. It's going to be more effective.
Is there anything out there like that? I think I was reading recently Brazil has some algae farms maybe for...
Yeah, as I mentioned, they have a plant in Israel, in U.S. They have a pilot plant, and also U.S. military began a large-scale production of biodiesel in 2010 for the jet fuel, for their
using
algae.
Also, I'd like to add to that there's approximately, they're doing research of 400 different species of algae, and there are a lot of algae that do grow in cold water and cold conditions as well, and they don't require as much sunlight. Because so there is, we do find that it's viable for 1% of flue-gas, but for 100% output of flue-gas, it's not as viable because the current technology is too costly for 100% output. Flue-gas. So.
What do you expect the market to be like for biodiesel at the price that you see it earlier?
Yeah, I mean, for biodiesel price at whatever we suggested, it has to be like significantly lower than what gas station franchisee would get from a refinery. So, like based on the current prices of diesel, like today morning when I checked, in some parts of New Brunswick it was over 140 cents. So that would translate to about over $5 a gallon. We are selling it at $3.50 a gallon, and this price of $5 per gallon has been, that trend has been going on for a long time, if not a year. So selling it at $3.50 a gallon is a fair deal to give to any supplier, and I'm sure they would consider it.
All right, this will have to be the last question.
Yeah.
As the little culture that you guys showed, there's a gypsum stream that's coming out, right?
Yeah.
Why do you guys just send it out? Why?
Well, that's a good question. The power plants right now, the SO2 reacting here is they have to remove it from the flue-gas stream. So that's the easiest way that they can process it without having a headache of sending the product that they can get from it. So the reason that they're selling that gypsum is that the gypsum is absorbing the moisture very fast, and the clients, they need it in the required moisture. So the easiest way is just to give it away, and nobody's gonna take that gypsum. But right now, J.D. Irving is buying that gypsum from taking the gypsum from the Belladune power plant, and that's reducing the cost of storing that gypsum, because there's associated cost with processing the waste, like this gypsum, which is stored in land in Belladune power plant. And well, there's a processes that you can do, like to make more profitable products from this SO2. There's a process called SNOX that there are two series of reactors that can produce a sulfuric acid from this SO2. But well, there is a cost associated with that. There is a capital cost with that, and also there should be a market for that sulfuric acid. And so there is and as we asked the NB Power staff in Belladune, they were considering making sulfuric acid, but that's another headache, and it's not their objective here. Their objective is to produce power, and maybe in future, if they want to further develop the process, they can consider making sulfuric acid out of SO2.
Thank you very much, gentlemen.
Thank you.